Hello and welcome to today's daily Leetcode challenge. Today we'll be solving question 1631, path with minimum effort. I'll be walking through my thought process as I come up with a solution, and then at the end of the video stick around to see me compare my solution to the solution of others. With that, let's begin question. Question 1631, path with minimum effort. You're a hiker preparing for an upcoming hike. You're given heights, a 2D array of sizes row times columns, where height row col represents the height of a cell row col. You're situated in the top left cell, 0, 0, and you hope to travel to the bottom right cell, row -1, col -1, i.e. 0 indexed. Okay. You can move up, down, left, or right, and if you wish to find the route that requires the minimum effort. A route's effort is the maximum absolute difference in heights between the two consecutive cells of the route. Return the minimum effort requiring to travel from top left to the bottom right cell. Okay, so in my own words, I'm pretending that this is a mountainous terrain, and I need to travel from one point to the other, making the least amount of climbs, the smallest climbs possible, right? And so in a visual, this would look something like this. We're given a 3x3 array, and we see that, let's see, this green path requires a maximum of, what is the difference between these two, 2, and 2, so must be 2. That must mean that for every other path, the absolute difference climb is greater than 2. And let's see what other ones are there. 1, 2, 2, 2. So this is a 3. This is a 2. Yeah, that works. Here, 1, 1, 1, 1, 2, 5, 5, 2, 5, 2. Okay, so the minimum height spike is 1. And finally, we have an example of just 0. Okay, so what's the thought process here? My approach is, it is definitely some sort of search, right? Either a BFS or DFS, because we do need to consider pretty much as many valid paths as possible. Now, what is considered a valid path is yet not determined, but what could be a valid path is a path where I am finding out that a climb happens to be better than what it's originally been. And that phrase right there should also give away that we need some sort of structure, intermediate data structure, that would tell us what is the current best climb to get to any sort of point. And that should be a giveaway that that is a dynamically programmable array. So a DP array, essentially, that represents all of these points and has the values of what is the best current climb from the starting point to that point. And so to reiterate now, we will either need a BFS or DFS algorithm, a search algorithm across this terrain, and then an intermediate data structure like a simple DP 2D array that would tell us what the best current climb is for each one of the cells. And I'm pretty sure that that's it. Pretty easy solution. Let's implement it. So we have a DP array for I in, let's say for row in the range len. Let's have max rows, len heights, max calls, len height 0. So we're first going to iterate over all of the rows, and then for, and then dp append, and I want to append, what value do I want to append? The worst possible case for a climb. And the worst possible case is basically just the biggest difference. So the biggest number that it could possibly be, and that is 10 to the power of 6. Okay, so that is going to be my 10 to the power of 6 for call and range max calls. Let's print dp. Let's also set dp of 0, 0, 2, 0, meaning that it takes us 0 to start, which makes sense, regardless of what the heights value for 0, 0 is. Let's see. Perfect. We have this pre-filled array now. Now, what do we need to do? We need to decide whether this is going to be BFS or a DFS. Well, in a DFS, we go head first, looking at all the, basically trying to find all the different paths from here, from start to finish, without taking into consideration what the neighbors are around us. Whereas for BFS, we at each point are considering what are the neighbors, what are our neighbors, and where could we end up climbing to. And so here BFS is the right approach. We do a BFS with a simple DQ. I'm going to put into the DQ my first point, because that's what I'm starting with, and a BFS looks something like this. While Q, I'm going to say point cur point is equal Q pop left, cur row cur column is going to be cur point, let's see, do we even need this right now? Cur point 1, and then, okay, so now we need to consider all different neighbors. So what are the possible neighbors that we can get? We could, I'm gonna write a quick function to do that. Def get neighbors. This neighbors is going to receive a point, row and column, and it's going to essentially pre-populate the result with different points. So if row is greater than 0, then I want to say res append the point row minus 1 column. If call is greater than 0, then I want to say res append row call minus 1. If row plus 1 is smaller than the length, then max rows. I'm going to say res append. There's probably a better way to do this. Row plus 1 column, and finally if call plus 1 is smaller than max calls, res append row call plus 1 return res. So that's just my function to get all the possible neighbors. And now for neighbor, in get neighbors of the cur row, and so again, just need to iterate over all of my neighbors, and here I will be deciding whether I should consider one of my neighbors or not, right? So my neighbor nay row nay call is equal to nay 0 and nay 0 and nay 1. And now, okay, now what do we need to know? We need to know what is the current climb and what will be the climb, right? So climb cur climb is just equal to df of cur row and cur column, but we need to consider the climb now. The climb is just going to be the max of the current climb, and let's see, no. The climb from current to the next is just going to be what? The absolute value of heights of cur row and cur column minus heights of, did I spell this heights correctly? I'm rushing again. Row and column. So this is going to be my climb, right? The absolute value. But what I have to consider is this value going to be if max, sorry, what is the, do I have to now take the max? I have to figure out if the climb to that new neighbor point is better than what it currently is. So climb will be a max of this and the current climb, right? Except, yeah, it has to be the absolute this plus this. And now if climb is smaller than dp of neighbor row and neighbor column, then I'm going to say that this is equal to my climb, and I'm going to say q append this this value, nay row, nay column, nay row, nay column, and return dp -1, -1. Let's see if that works. I have 4 minutes before cur row column before I now what did I mess up? This is 1. The current climb is how long it took me to get to the current point, and that's correct. dp of current row plus current. The neighbors is also done correctly. Row call. I'm consistent everywhere. This seems to be right. Row call. Let's see. Where did I mess up? The current climb is how long it took me to get to the current point. Cur row, cur call. The climb that I'm considering is the max of the absolute of the heights, current row, cur column, minus the neighboring, right? Right. Let me try this. Okay, quickly submit. Okay, I think what was happening there is okay. What was happening there is the climb. I don't have to consider the cur climb into this thing here because it is already part of the current call, right? So that is already going into this calculation here. So basically the current climb here was irrelevant. Yeah, okay, cool, that's it. Let's see. So not a fast solution, but definitely an appropriate one. Let's see. Where this could be going wrong. So that's definitely a better way of doing the plus considering or creating its neighbors. I'm really just looking here for anything and any different approach rather than yeah, so this is drastically different. There's no dynamic programming. DP array, BFS with heap, min effort. Wow. Heap pop. Okay, clearly my approach isn't the best. I'm going to stick to it though for now, and yeah, I Dijkstra's algorithm here to find the minimum shortest path where the edges between nodes are basically just the weights, the differences between them. So yeah, that makes sense too. But I don't know how to do that. So okay, I'm gonna end it here, and I guess I have another video to make about the Dijkstra's algorithm. Cool. So yep, thank you for watching. Hopefully this is at least intuitive. It was very intuitive and natural to me, but fortunately it wasn't the fastest. Anyway, okay, well, thanks for watching, and I'll see you later.